Time to talk about Postgres at scale at scale. So today I'm going to be talking about how to manage your tuple graveyard. Postgres bloat seems to be one of the topics of the hour. There are several different talks around different areas of that here at Scale. And I would say that among those, this is probably the most from the ground up talk. It's what is it, how to manage it, what does it mean for you at a high level. Before we get started, I'll introduce myself. Like I said, my name is Chelsea, and I work as a software engineer at Brex. If you're not familiar with Brex, we're known originally as the credit card for startups, is the tagline. And these days, we do expense management software as well. We're a pretty large Postgres shop. I'm currently the tech lead of the data storage team, and we manage over 200 Postgres databases, mostly on AWS. And there I work on Postgres infrastructure, query optimization, and just about anything else people ask of me in that space. Getting started about what we're going to learn today. Again, my goal with this is to talk about Postgres bloat, but that's the end destination. In order to get there, you kind of have to go through this forest of some Postgres internals to be able to really understand what it means to you. So I'm going to start out with MVCC and learning about vacuum, live versus dead tuples, etc. And we're going to move from there on to table bloat. What is it? What causes it? How might it impact you or not impact you? And then moving on to how to quantify it, mitigate it, and avoid it in the first place, which is always the goal. Finally, we're going to finish off with talking kind of a step above the entire conversation, leaving the extensions behind and thinking more about how to design bloat-aware data access patterns from the start, beyond just reconfiguration. So without further ado, let's get started. So we're going to start out with Multi-Version Concurrency Control. What is MVCC? Multi-Version Concurrency Control is really just a set of rules in Postgres. And the point of this set of rules is to provide two seemingly contradictory features, the first being transaction isolation, and the second being fast performance. And why are those things actually contradictory, though? It seems like they wouldn't necessarily have to be. So the first thing, transaction isolation, is the I in ACID, if you're familiar. ACID is an acronym that we use in the OLTP database world to describe atomic, consistent, isolated, and durable. These are what we describe being a transaction being a unit or process of work that we're going to perform on the database, that you perform kind of as one unified chunk. There can be more than one command in it, but we're going to execute it on the same version of the database. And in transaction isolation, we want data within the transaction to be representative of table state when it starts. Things may change or not change depending on what version of transaction isolation you're creating, but it needs to look like the table did when you started this. The second thing is fast performance. There's not a ton here to say. It's kind of self-explanatory. In slightly more technical terms, you don't want writes to block reads, and vice versa. Reads also shouldn't block writes. We want to specifically think about concurrent fast performance, because I would say transaction isolation is easy and can be performant if you have one reader and one writer. But how often is that the case for us in 2023 or even 10, 20 years ago still? These goals are contradictory because locks, which are necessary for transaction isolation to some level, can lead to this cascading pattern of locks and waits, and by extension, bad performance. If you think about it from a high level, if you imagine like the most basic version of a lock, where you say, okay, I'm writing now, it's my turn, locking this database until I can finish, then everything else that would need to write would need to queue behind it. Everything else that would need to read would need to say, well, what version can I read from? What's the current state? And then you would get into a very non-concurrent situation, which is not what we want to do. MVCC takes an approach that focuses on the first two letters of the MVCC acronym, which is multi-version. Basically, to achieve these two goals, it does row versioning via tuples, or tuples, dealer's choice. As the dealer, I'm going with tuple, and I'm going to say that a tuple is the internal representation of a row version stored on disk. You can sort of think of a row, quote unquote, as a logical construct only. It's an idea. When we run select star from this table, we see rows, and really each row is this concept that represents 1 to n tuples under the surface. I sometimes think of it or describe it to people as like a row is almost like a front end or a GUI. It's just something that you see, and underneath the back end of it is a number of tuples that describe that data, how it changes over time, whether it's updated, deleted, etc. There are 2 types of tuples, live tuples and dead tuples. A live tuple is the newest row version of that data, or a row version that's still being used by something. So even if it's outdated, there's maybe a 30-minute select query running for analytics purposes. That row is still necessary because that query needs that version at that time. The other option, dead tuples, which is what we're talking about today primarily, because we're talking about our graveyard of tuples, is everything not covered by live tuples. So it's a old row version and an old row version that is not being used by long-running queries or any query at all. You can think about sort of like, well, what's the use case for that? Not really anything. It's not being used for a live query. It's not the most recent version. It's not something we need anymore. As part of MVCC, all DML operations, which is insert, update, delete, create new tuples or update tuple metadata only. We aren't doing what we would call hard deletes. So it's when you're deleting the actual row, that's not what happens. Instead, you're always inserting or updating. But I think this is better visualized, or I think this is better worked in when you think about how snapshots work. Snapshots is sort of the second part of MVCC. So like I said, first of all, we're always inserting or updating metadata, but every transaction has something we call a snapshot. It's an in-memory data store that's created on a per transaction basis. So we're starting a transaction, let's say a select. That transaction needs to know what the database looks like at that point in time. And in order to figure that out, there are 3 fields that the snapshot needs to know. It needs to know more or less 3. It needs to know xmin, xmax, and xip list. It uses this information to figure out what version of the data is being seen by your current query. On any given tuple, xmin is the transaction ID that inserted it. Xmax is either null, meaning it hasn't been updated or deleted, or the transaction ID that did update or delete it. And then there's one final field, which we'll kind of circle around to in a couple slides, xip list, which is a list of transactions that are currently still running that can be sort of oddities. They kind of break the idea of, easy, it's within this range, sorted, this is what you see. It's important to note that transaction IDs are assigned at the transaction start. So that's what makes xip list important, but again, I'd rather skip forward a couple slides for that because that's going to be a lot more easy to understand then. Let's go through an example to understand how this works in a more real way. Using this table as an example, let's say we have some employees at a company or just people in the US or outside of the US, and we're having an ID column, a first name, city that they live in, and updated at. So when did they live in the city, have they moved, etc. And in gray on the left, you can say xmin and xmax. Again, xmin is the transaction ID that inserted that tuple, and xmax is either null, meaning it hasn't been updated or deleted, which all of these were inserted by the same transaction ID and are currently live, or nothing. The first thing we want to do is insert somebody new. So we're adding somebody named John to the database. He lives in New York, and this was updated, or he moved to New York, I guess, in 2002. You can see that our current transaction ID for this insert 600 has been added to xmin. If we update John, John's going to move to Seattle, because Seattle's great. We can see that we make the original tuple, his first tuple, a dead tuple, and we do that by assigning the transaction ID of the update to the xmax for that tuple. Right afterwards, we're inserting a new tuple afterwards. This is part of the same transaction, so there's no way to kind of query and see this in-between liminal state, because we're dealing with 2 tuples here from a user perspective, but under the hood, this is what happens. Any update is just a delete and then another insert. And the xmin for the new secondary tuple is the transaction ID that deleted the first one. Rounding it out here, we have a delete. What happens in a delete? All we do is we update the metadata of our second tuple, just as we did with update. So we assign our current transaction ID to xmax. Awesome. So that seems great. We figured this out. Does this mean that we're just infinitely increasing row count forever? We're doing soft deletes. That kind of solves the latency problem, and it solves the consistency problem, but what do we do from here? The answer is, as many of you guys are probably familiar with, is vacuum. Vacuum has a number of pretty important jobs, and the one that's most critical to table bloat is the first thing on this list. It deletes dead tuples from existing Postgres pages, which frees up that space for reuse. But beyond that, it does a couple other things. For example, it updates Postgres internal stats via running analyze at the same time, which means that you can improve the query planner's effectiveness. It also updates something we call the visibility map, which I won't go into a ton of depth in here, but it helps future vacuums run more effectively and also helps index-only scan performance. And finally, it frees up transaction IDs for reusability to avoid transaction ID freezing, which by extension avoids wraparound. If we ran a vacuum on our example, what would that look like? Like I said, it frees up the space for reuse, so those two places in the page are still there, they're just now empty. They're now available to be added on to. So new processes, new transaction IDs can use that free space to insert new data. Now that we have this free space, there's kind of one edge case. I said earlier I was going to cycle back to this idea of how concurrently messes with things and why we need XIP list. Let's say that we're going to do two commands now. We're going to insert, and then we're going to select. We're on transaction ID 611, and first we're going to insert something. We're inserting Olivia, who's going to live in New York. That's assigned with xmin of 611, because that's a transaction ID. For whatever reason, this insert is going to take a very long time. Maybe it's CPU resources, maybe it's only one row of like 50,000 that needs to be added, so it's going to hang and hang and hang and figure that out. But for whatever reason, this is a very long process. Because the 611 transaction ID is assigned at transaction start, that's visible. But while that's running, if we start a second separate process, a select star, this snapshot for the select star is going to see that, okay, well, I should be able to see everything from 611 plus, but because 611, or that transaction ID, is a currently running process, it's not committed, this is an oddity. I'm going to track it in XIP list, and I'm going to judge whether or not this is visible in the select star based on what the status is when I'm ready to actually finish the transaction. In this case, if it was still running and the insert ran longer than the select, then that would mean that it would not see that. And finishing up this first section, I want to make an important note on Postgres disk usage. Vacuum, as I said before, frees up space for reuse. Without explicit intervention, Postgres disk space will only increase. So pages will be added, but not deleted. Vacuum will delete the tuples within the pages, but like you could see, it left these kind of, at least visually, these empty rows, empty spaces for new rows or new tuples to be added. It didn't actually reduce disk size. There are minor exceptions to this, which apply to only like 1% or fewer of cases, where pages can be truncated from the very end of the heap, but that is overall quite rare and something I'm not going to focus on in this talk. To define page a little bit more specifically, page is the smallest unit of disk space. By default, they're 8 kilobytes in size. You can increase it, but I would say the use cases are relatively limited. Overall, what it stores, you can see in the page layout example, are heap tuples is the number one thing. That's the big free space, the white there. And page header data at the top, which tells you, okay, I've accessed this page, now where do I go for this tuple? And then line pointers, which are just the arrows, which help you get to that tuple with greater efficiency. So before I go into the next part, are there any questions so far? Fantastic. Then I'll continue on table bloat, because that's the title of the talk, or something like it. Table bloat, and I'm stealing this definition from Lucas from PG Analyze, because I thought it was very good, is less than optimal page density. By page density, I mean the number of live tuples per page versus how many could hypothetically fit in that page. An example visually might be something like this. If a number of pages or a table has high page density, it might look like the top. You have 10 tuples, those gray lines, and they fit in 3 total pages. Versus the same number of tuples on the bottom, still 10 tuples, but there's a lot more space per page. The density is lower. So if I ran a select star, the top would need to scan through 3 pages, whereas the bottom would need to scan through 7 to get the same data. Why is bloat often problematic? With dead tuples occupying what should be disk space or page space available for new tuples, it'll just basically continue to create new pages. It'll append page, append page, append page, when in reality, it'd be really nice if vacuum could clear out the existing dead area for reallocation. So this increases disk usage, but I would say that way more important than the disk usage part is actually the increased I/O. In our current world of lots of managed services and also just lots of fast drives, I/O usage can still be very expensive. So after vacuum runs and dead tuples are deleted, live tuples are stored sparsely, like I said. So the number one thing is what I came back to about the idea of doing 7 pages for the same scan, what you could have completed in 3. And over time, that can lead to very bad outcomes. But I said often problematic. And I would say that things are problematic when they create problems. It seems a little simplistic to say, but I would say that bloat is the root of other problems. It's not a problem within itself. So if you don't have any downstream effects from bloat, it's not a good thing. It's not improving your database, but it's actually semi-neutral. It's like a dark horse could become an issue, but so far, it's not actually leading to downstream effects. Downstream effects that you might see from bloat, which make bloat worth addressing, either proactively or reactively, would be things like bad read latency, which you would see from the increased I/O, high, maybe expensive disk usage, and also high, potentially expensive IOPS, especially in systems like Aurora, where you're charging by IOPS. I have seen people want to address table bloat for this reason, because it can be an actual reduction in your price as well as your resource efficiency. Bloat occurs through 2 primary ways. The first is having update or delete heavy workloads. Because bloat is at root cause caused by this influx of dead tuples taking up lots of space, updates and deletes, as we said, those are what create dead tuples. Inserts just add them. So bloat is caused by pages becoming saturated with those dead tuples. Some examples that I've seen that might be common update and delete heavy workloads would be user activity that results in lots of cascading updates and deletes, or scheduled batch jobs, which may update massive or delete massive amounts of data in one big go. Secondarily, in combination, it's really these 2 in combination, not just one of the 2, would be badly tuned autovacuum configuration. Overly conservative or just old or default vacuum configs paired up with that update delete workload can mean vacuum can't actually catch up. So you can have one or the other of these and it can pretty much be okay, but add them together and it can create table bloat. An example case study, which I've actually seen separately at multiple organizations, is something like a machine learning feature store in Postgres. Often, data science prefer to have this data in Postgres, despite it maybe not fitting the exact archetype, because then they can do things like export it to Snowflake, export it to Redshift, run analytical queries, use SQL standard language in a way they can't if it were stored in something like DynamoDB or a document store. So let's say that we have hundreds or thousands of features per user, and we have this table here where we have a feature name, something like last login, owns house, whatever, and then a user ID related to that feature and the value that user has. We might have a unique constraint, so we only want them to ever have one value for likes cats, which means that when we insert this, if it's a new user, we're going to insert it. And if it's an existing user and they're updating, they say, okay, I didn't like cats and I'm going to update to likes cats. That's an upsert, which is really saying insert if not exists, otherwise I'm going to update it. And of course, updating creates a dead tuple. If we have this table at about 300 gigabytes, all writes are upserts, and we have burst-based high volume write traffic triggered by user activity. You log in, you do a bunch of stuff, updates a bunch of features. And maybe we even are super helpful. We love our data scientists. So we want to be able to deprecate features. And we wanted to have a cron job-based process to remove old values. So we want to deprecate owns house. 1 out of 1,000 features, so we go and we run a delete job to run 1/100th of, or 1%, better said, of our 300 gig table and default autovacuum configs. The problematic part of this are pretty much the parts in red. You can have this 300 gigabyte table, fine. Hundreds of thousands of features per user, fine. User activity, also fine. It's the combination of all things in red that I would say makes this a problematic workload. It's the feature deprecation using something like a mass delete, not tuning autovac configs to be used to this workload, and also the upsert pattern. The upsert pattern especially can be problematic for a number of reasons, but leading to bloat like this, especially in a high write volume database or table, is going to cause issues. Any questions before I continue? Cool. Now on to quantifying, mitigating, and avoiding table bloat. There are a couple ways to quantify how much table bloat you might have. Once you figured out, using a lot of I/O for this, or if you looked at that last example and said, wait, I'm doing that, got to figure that one out, then how do you actually figure out how much bloat you have? There's a couple ways. The primary ways would be through pgstat tuple, which is a Postgres contrib module, which addresses this and a couple other specific use cases very similar to it. This returns a precise value for how much bloat you have, but can be very expensive. It does a full table scan, and it needs to look over, it needs to do a sequential scan. It's not running an index scan. So it can be slow running and also has high resource usage. Basically, it runs an O of n runtime based on your table size. So, if you're coming in and you're using your 300 gigabyte table to figure that out, because usually you actually need to use it on larger tables, it can be quite taxing. The other option is estimation. So as the name kind of suggests, this is the idea that we're not going to get our actual return value. It's not going to be a real value. We're going to estimate it based off what Postgres roughly estimates are the number of live dead tuples, the number of rows, period, in our table. There's a bunch of open source queries, mostly available on GitHub, that leverage internal tables or fields, such as pg class rel tuples. When you do this, you always want to run analyze first, which will refresh your internal statistics and make the estimation more accurate. But it will always run an O of 1 runtime, because you're just fetching from these internal stats. So this doesn't use the same resource usage, but at the same time, you're not going to get the same accuracy as you would with pgstat tuple. If you run pgstat tuple, it will return a value like this. At the top, or I've put in yellow the things I think are more relevant, you have the table length in bytes, the number of total live tuples, the percentage of total tuples which are live, in this case 90%, and the percentage of tuples which are dead. You'll notice, if you do math or are looking at this, that the math does not add up. So you can see that we have the live tuple percentage here, or can you see my mouse? Apparently not, doesn't matter. You have the live tuple percentage there, but that added on to the percentage of dead tuples does not equal 100. That's because we have live dead and just free space. The point of vacuuming is to create more free space out of our dead tuples. But even with that, we don't always exactly equal 100. There's some minor reasons which I won't get into here, like fill factor and stuff like that, but that is expected. I would expect maybe 1 or 2% off max is about what you would expect to see with pgstat tuple. Yeah, you can see the thing you're mostly looking at is dead tuple percentage here. So what percentage of our total table space allocated in pages is held by tuples we have no use for. If we were to do the other option, estimation, it would look something like this. You would first analyze verbose to see your output, get some stats on it back, and then run some really long query that you get from the internet and check over to make sure it's not doing anything too insane. This is a truncated response, which I kind of formatted to look a bit more similar to the other one. There's more fields. But what it will return to you, if you use one such as the example below, which is probably the most popular, you would see estimated table length in bytes, size of table bloat also in bytes, and percentage of real size, the first row there, used by bloat. And again, you're looking at bloat percentage here. If you compare these two methods, you may have noticed that they're actually not very comparable. The first one, your pgstat tuple, where you're getting real numbers, you're looking at percentage of dead tuple count. What number of my tuples are dead? versus the secondary, you're looking at disk space. What percentage of my disk space is held by dead tuples? That's why I would not recommend comparing the outputs you get, because they can be quite skewed. You're looking at how much disk space is used versus how many tuples do I need for this. Tuple size can vary wildly, and post-page level opportunistic pruning leaves 4-byte tombstones, which might have the result of throwing this off in a pretty heavy way. So for example, if it's leaving a 4-byte tombstone, you might have 1 kilobyte of dead page space, but that could be 250 tombstones or 250 dead tuples, or it could just be 10 100-byte tuples that have not been cleaned up yet. If you want more info on this, a more relevant talk would be a talk that happened earlier, so either just magically have been there or watch the recording, that being Bloat and Postgres, a Taxonomy by Peter Gigan. Now on to the big question, how much is too much? We've seen numbers, but that's kind of the relevant question. It's almost annoying if you go to a talk and they're like, okay, how much? And you say, that much? I don't know, some? But unfortunately, it really always does depend, which is an irritating truth about Postgres in the world. So there's no number I can say, after this amount, you are absolutely too far off the mark. However, I do have some numbers that are my personal rule of thumb. All of these are about individual tables. From dealing with very high bloat tables and the fallout from it, my personal opinion on this is that very small tables, a gig, maybe 2 gigs, kind of doesn't matter. Again, it's about the end result. What's the actual impact on you? 70% is fine. I've seen more and it's fine. It's not ideal, but that size, it has a really imperceptible impact on performance. And as you get bigger and bigger, you expect it to be smaller and smaller. What I would call a small to medium table, which is, I would say, most production tables, 1 to 30 gigs, up to 25% is fine. Large tables, 30 to 100 gigs, I would say 20% is acceptable. And very large tables, which is anything above 100 gigabytes, I would aim for 18% or less. Lesser is better. Usually, you still want to have free space. But when you're dealing with these really large tables, you do expect to have a lower percentage, because if you're thinking about 100 gigabytes size table, 18% of dead tuples is 18 gigabytes of space. And it's really possible to configure it so you don't get this in the first place. So anytime you see that gold star, it means the caveat is, this is my opinion, it depends, don't sue me. How do you deal with bloated tables? There are 2 things, configuring autovacuum from the get-go or later on, as well as repacking and rebuilding tables. Configuring autovacuum to deal with bloat usually means you're going to configure it to be more aggressive. By aggressive, there's kind of 2 sides of aggressive. You either can mean aggressive, you mean autovacuum runs more frequently, or you can mean autovacuum runs at a faster rate. So you're either taking the brakes off, or you're just telling it to run all the time or more than it currently does by default. The number 1 thing that you would probably change would be autovacuum vacuum scale factor. By default, this is set to 0.2, meaning 20% of table size. And what this basically means by default is that 20% of the table must have changed since the last vacuum ran for autovacuum to be triggered. So the smaller you make this configuration, the more frequently it will trigger. If you have a large table, this should probably be configured, because if you go back to our previous example, at a 100 gigabyte table, if you're keeping the default configuration, that means that 20 gigabytes, or I guess, again, space is not equal to tuple count, but 20% of that 100 gigabyte table will need to have changed in order to trigger it, and that is far too much. Something that I've seen suggested and have personally done myself is for large or very large tables, scaling this down to be about 1%, so 1% of tuple size. Alternatively, you can use autovacuum vacuum threshold. This is by default 50 and is basically added on to the above configuration to trigger that. Usually I would say there's only one way that you touch this, which is because it's mostly scale factor you want to configure, is if you want to forget about the idea of ratios altogether and just trigger autovacuum when it hits some certain number. So for example, what you can do to that is do autovacuum scale factor of 0 and say, doesn't matter what percentage, doesn't matter how much I grow, let's trigger vacuum every 200,000 updates or deletes, dead tuples. And also with these two, you typically want to tune it on a per table basis using alter table. You can imagine if you have a system that has one massive table and then a couple smaller tables which are used to join or provide some config info, you're not really servicing those small tables if you're configuring your entire server to fit the kind of worst case scenario. You might be doing too much for those smaller tables. The second thing you can do to configure it more aggressively is by changing these two. These two, the first one is autovacuum vacuum cost delay. If you're PG11 and up, you can leave this as default, it's 2 milliseconds. If you're before and on modern hardware, you should change it to the current configuration, which is 2 milliseconds. Basically, this is the cost delay or wait time used. So this is used to artificially slow the vacuum process. Basically a wait time that says once you reach this level of resource usage, back off for a second so that autovacuum doesn't steal a bunch of resources from other things that need resources. But with modern disk, modern Postgres configurations have caught up to that, and they have started to assume that you have better hardware. That you have SSDs or NVMEs. And so pretty much any version of Postgres, you can be using that 2 millisecond config. Secondarily, autovacuum max workers. How many vacuum processes can be running concurrently at any one time? The default is 3. This is usually fine. And even for big tables, autovacuum, there's only one autovacuum that can be running on one table at any one time. So if you have your massive 300 gig table, increasing autovacuum max workers isn't going to help that. This is something where if you have maybe thousands of tables, and you're noticing, you can look in pgstat progress vacuum and you see, oh wow, we're pretty much always running all 3 of our workers. Then you might want to start tuning up +1, see how it goes, see how your overall process reacts to that, and consider that as well. The second thing you can do is repack or rebuild tables. The native vanilla Postgres way of doing this is it's vacuum full. This is not recommended due to the extremely heavy lock, which is access exclusive, which means that running vacuum full will block all reads and writes to your table. This will return the wasted space. I said auto vacuum will not return your pages, it'll just free up tuples. This is different. It actually completely will rebuild your table, and you will look at disk space afterwards, and you'll see system level disk reduce. So that's good, but kind of not worth the trade-off for most systems. When you used to see things like this, is mostly, 5-10 years back, or still today, if you're maybe at like banks or something, where they'll have their 1-hour maintenance window every Saturday at like 3 a.m. Sometimes they're doing stuff like this. But what they could do instead is using extensions such as PG Repack or contenders such as PG Squeeze. I'm going to talk about PG Repack, because that's what I've used, but I'll compare to PG Squeeze as well. Which will duplicate the bloated table, copy over incoming data via triggers, and then alter it under the hood, basically switching them out. And once it switched them out, then it will drop the old bloated table and leave the newer, fresher one in its place. This takes an access share lock, which is very minimal, and will not impact your readers and writers with the exception of maybe DDL changes, so like adding columns to that table during that process is out of the picture. It will require 2 times roughly the current table size and disk, because again, you're duplicating it and then dropping the old one. And it will use a lot of CPU and RAM, so it's best done conscientiously, I would say. Personally, I have found it to be occasionally flaky. Hopefully you never run into a situation where someone just kills the PID of the process, but that actually has happened to me before. And the good thing is, though, even in a flaky case, what you'll see is that the worst case scenario is not so bad. So in the worst case scenario, someone cancels the back end of your PG Repack process. What that means is that you leave all these half-built, orphaned tables just in the wild. And your existing table is still working. So there's no data loss. All it means that you, as database administrator, need to go in and drop those tables manually, because they're going to be in the PG Repack schema. So you just got to clean them up, try again, and tell everybody else to stay away. Overall, I would say this is definitely recommended for use. It's not the ideal solution. Again, the solution that's best is just don't run into this in the first place, but that's easy to say and maybe harder to do. Comparing it to competitors such as PG Squeeze, I think is also worthwhile. Again, I've only used PG Repack personally. PG Repack, you have to create an extension for it, so just create extension, and then you run it from an external client, as showed as an example before. So you can target it at your entire database, but realistically, you should be targeting it table to table at a time in like almost all scenarios. It has it's an external binary, overall less invasive, and because it's an external binary, it's supported in managed Postgres services. So it works with just your vanilla Postgres plus an extension. PG Squeeze, and I think there are others like it, are different. So it operates entirely within the database. So it's nice because you don't need to run anything from bash or anything like that, which can sometimes be a little bit annoying. But on the other side, it's not supported by anything like RDS because you're going to be actually editing the real binary of Postgres. And it has some additional benefits, like, for example, you can schedule repacks on a regular basis, which you can't do with PG Repack. It seems useful. But overall, I would say it's kind of the trade-off you see a lot in coding. Either do you kind of let it have its own mind, and do you change the default? You stray away from the vanilla installation, but with more features. Or do you stay a little bit more vanilla and decide you're going to manage it yourself? Before I continue, any questions? Yeah. With what? Play well? Ah. Yeah. The question was, does PG Repack play well with tables that have foreign keys? And the answer is yes. I would want to double check and run that myself before I tell you to do it like now and pull out your laptop, but it does. It's quite feature complete overall, and like I said, the only problems I run into, despite using it with foreign keys, etc., is the idea that it needs to be triggered externally, and other than that, feature complete works for me. I'll check up on that more later, but I've never run into any issues with that. Anything else? Cool. So we're going to finish off here with one final section, which is going to be kind of stepping up a level. We've been talking about extensions and queries you can run and some internals about Postgres, but the big question, in my opinion, is actually how do you avoid this? And how you avoid it is typically from a human level. Discussing database access patterns isn't always sexy or fun, but it is how you avoid this stuff and how you communicate with other developers and engineers on your team. The most important thing, I think, is to have a conversation about how, when, and for what purpose are you reading and writing data. Answering questions ahead of time with your table, such as, well, what percentage of transactions will be reads versus writes, will help you figure out what kind of issues you might run into down the line. Also, discussing with teams or with yourself, roughly what percentage of data growth do I expect annually? If you can just do some basic multiplication, well, okay, well, we're growing about 20% users, about this much data per user, what do I see this as being as? And you can run into some really surprising answers that might lead you down a different path. And finally, this is more from a DBA perspective rather than the perspective of a developer who also kind of acts as DBA. What sort of access will you and won't you support? If you're acting as a DBA, what is appropriate for developers to be able to build on Postgres versus not build on Postgres? And what's your process of enforcing this? I'm going to go over some high-level things that are good ideas to think about in various scenarios. So, okay, if you have an update and delete heavy application, the theme of this section is going to be maybe just consider how you can do things differently, because the easiest way to avoid bloat is to reconsider how much data you actually need to write to Postgres. A lot of the time when I work with people or when I work with developers inside the organizations that I work with, the way that they're able to stop this is by reconsidering, oh, well, we were actually, writing in this way, but we can actually just change our code, and, what do you know? That reduces our writes by 30%. And that is often the most effective way, beyond tuning, to actually get to a better state. Some examples that you might see here are users' actions triggering a burst of updates for a single row. Something you might consider is, can you update each row once instead of n times? A way that I see this done is by, if you have something like Kafka, consumers writing into Postgres can use a Kafka Streams or something to kind of combine them into a single write, or can you just batch it? How are you doing your application logic to be inserting into this? Another anti-pattern I see leading to this sort of pattern is updating the same row, for example, last seen many, many times. Reconsider, maybe is it appropriate to have an append-only log style table with just inserts? So you're not generating the same dead data, the same dead tuples, index on the user ID and when it was inserted at. And so instead of selecting distinct on, for example, your machine learning feature example, your feature name and your user ID, instead you get the most recent of probably several rows for this. This, I will point out, does introduce new problems. Now you have a potentially unbounded size table, which we'll discuss in a future slide. But this is something that I have seen be very effective for avoiding this particular problem. And another example, if you have upserts, as I mentioned, oh yeah, I already kind of said this one. If they originate from a queue consumer, I often see a problem of causing hot rows or lock contention. Imagine using our example that you log in, you do a bunch of stuff in the app, it triggers all these writes. They're all going to be writing from my user. During that time, I'm going to see probably several updates for those specific rows over and over again. The difference between updating a bunch of rows in the same row once. Can you design your queue, if you have this queue, so that the updates and deletes will only be processed by one consumer? For example, if you have, again, Kafka, if you have partitions, if you partition on user ID, then that means that at the very least, you're not going to trigger all these writes, which are going to stampede over each other, causing lots of waits. Instead, okay, well, at least they're going to queue in this one consumer, and you won't cause the same amount of locks and lock contention. Another kind of anti-pattern, if you have these large delete jobs, can you reconsider, first of all? But secondly, is your data set compatible with partitioning? Meaning you can replace delete with, that should be detached partition, and something like pgpartman. Partitioning is not in one big solution for every table over 100 gigabytes. It requires thinking such as, is there a natural partitioning key? Would it make sense to use a range partition or a hash partition? It's not going to work for every scenario, but if you have a very large table, it very well could. Are you able to always provide your partition key for user queries? If so, then it's a great idea to start here. And if you do what I said in the first slide, where you're thinking about how fast is my data going to grow, you might come out to a solution that says, oh wow, I'm actually going to have, this table should be 700 gigabytes in the next year and a half. In that case, when you create it, you might actually be able to start partitioned and communicate to developers that they need a feature or the access pattern that you are providing is always providing the partition key. You expect and say, hey, this table is going to perform in this way, and we expect and we enforce the idea that you need to provide the partition key. And are you able to always use a reasonable batch size when you do deletes instead of just one huge transaction? That can help as well, just for general database health. And finally, instead of doing one huge delete job every week, maybe, okay, delete the last week's data, can you make it smaller? Can you make it incremental, where every day we run smaller delete jobs, so 7 deletes versus 1? This is sort of a general best practice thing. It's not just for bloat, but if you do this, then you can also configure and orchestrate autovacuum with it. So say, okay, well, I think I'm going to delete about 300,000 rows or less each day instead of that times 7. Then instead, maybe you can trigger autovacuum so it runs after about that much. So you're able to kind of do it in smaller, more incremental steps. Final question being, are you reinventing any wheels? Wheels can sometimes be reinvented, and this one you'll notice has the gold star making a comeback. This is my personal opinion. My personal rule of thumb is using Postgres for things outside of its intended wheelhouse, which is generally OLTP databases. I come back to the example of like a profiles table or something like that, is actually fine most of the time. There's tons of community-supported extensions. It also just has really strong functionality, especially in more modern versions of Postgres. And what I usually say is that Postgres supports big data with a little b. Hundreds of gigs, fine. I've worked with like 2-3 terabyte tables, fine. But it's not going to be as performant as you start to move those data access patterns to a less OLTP-friendly pattern. So for example, full text search. If you have 25 gigs of data, Postgres is cool. More than that too, if you optimize it and you have somebody who knows how to work with that. But if you have 100 gigs and you're querying it in a way that's not natively supported by Postgres, Elasticsearch might be a better call. And even if you don't need to use Elasticsearch, you'll probably end up putting your Postgres DBA through some serious effort and giving them a bit of a low bus number, so it might be a good thing to consider. Similarly, the key value store. I've seen Postgres used as a key value store many times, and it's not bad. But there's a big difference between a 50 gig key value table, where 80% of the traffic is reads, and an 80 gig key value table, where 80% of the traffic is writes. And a lot of that difference is bloat. That concludes my presentation today. I hope it's enjoyable, and thank you very, very much.